Lesson 1.5 covers an introduction to probability. A probability experiment is a chance process that leads to well-defined results and outcomes. You can think of the probability experiment as the action that's performed. An experiment might consist of more than one action. If the process is repeated one or more times, each time it's performed is called a trial, and the experiment consists of all the trials. An outcome is the result of a single trial of a probability experiment. Let's look at some examples. Let's say our experiment is flipping a coin. That's the action that we're doing. Well, the possible outcomes for flipping that coin, the coin could land on heads or it could land on tails. If our probability experiment is a baseball pitcher throwing a called pitch, well, the possible outcomes, the pitch could be called a ball or it could be called a strike. And the last example, if the probability experiment is selecting a digit, well, the outcomes are all the digits. So we have the numbers 0 through 9. Well, probabilities are basically ratios. So before we look at what a probability is, let's consider the parts of the ratio. The first part is the sample space. We talked about this in a previous lesson. The sample space is basically the set of all possible outcomes for a trial. So the sample space for rolling a fair die, if you roll a die one time, you could land on the numbers 1 through 6. So the set of numbers 1 through 6 become our sample space. The sample space for tossing a fair coin, if you toss a coin once, it could land on heads or tails. So our sample space is the set containing heads or tails. If we want to list the sample space for tossing 2 coins, this time I'm just going to use an H for heads and a T for tails. Well, the first outcome, both coins could land on tails. So I'm going to write TT. Another possible outcome, the first coin could be tails, the second coin could be heads. So I'm going to write TH. Another outcome, the first coin could be heads and the second coin could be tails. So I'm going to write HT. And then finally, both coins could land on heads, so I'm going to write HH. Well, in most problems like the previous ones, the sample space is easy to list. From time to time, the sample space is not that easy to find. When this happens, we need to use methods to organize the outcomes to make sure we have considered every possible outcome. And we looked at these 2 methods in a previous lesson. One method is a tree diagram, and another method is creating an organized list. For the following examples, let's just focus on the number in the sample space, and then we'll list the sample space. So suppose you have the sample space for a couple having 2 children. Well, first let's find the number of elements in the sample space. So I'm going to abbreviate the sample space with an S. So the number of elements in the sample space. Well, first consider the first child. With the first child, there's 2 outcomes. It could be a boy or a girl. So I'm going to put 2. For the second child, I have 2 outcomes as well, the boy or a girl. Well, these are independent, so I'm going to use the multiplication principle that we looked at in a previous lesson. And I'm going to multiply these, so the number of elements in my sample space should be 4. So let's list those. I could begin by having both boys, so I'm just going to write BB. Another option, the first child could be a boy and the second child could be a girl. So I'm going to write BG. Then I could have a girl followed by a boy, so GB. And then I could have two girls, so GG. Now let's look at the sample space for having 3 children. First, let's find out how many options we're going to have. So since I'm having 3 children, I'm going to draw 3 blanks. Each time I have a child, there's 2 possible outcomes, a boy or a girl. So I'm going to put a 2 in each of those blanks. If I multiply those, I get an 8. So the number of outcomes in my sample space is going to be 8. There's 8 possible combinations of boys and girls that I could have if I'm having 3 children. So if I list those, I want to do so in an organized manner so I don't leave any out, and that's why it's helpful to know how many they're going to be. So let's first consider the option of having no boys. If I have no boys, then I have all girls. So GGG. Then I could have 1 boy. So that means I'm going to have 2 girls and a boy. Well, I could have the boy first, I could have the boy second, or I could have the boy third. So this gives me 3 options or 3 ways to have 1 boy. Then I could have 2 boys. Well, if I have 2 boys, then that means I have 1 girl. So I could have the girl first, the girl second, and the girl third. And in each of those options, I have the 2 boys. And then finally, I could have all 3 boys. So this gives me my 8 outcomes for my sample space. The next example is very similar to the last one. I want to list the sample space for tossing 3 coins. Well, again, find the number of elements in the sample space. I'm tossing the coin 3 times, so I'm going to draw 3 blanks. Each time I toss the coin, there's 2 possible outcomes, heads or tails. So if I multiply these, I get the number of elements in my sample space, or the number of possible outcomes, is 8. So I'm going to list these the same way I did the boys and the girls. Let's start with no tails. If I have no tails, they're all heads. Then next I want to list the options for 1 tail. Well, I could have that tail appear first, I could have it appear in my second toss, or I could have it appear in my third toss. Then I could have 2 tails. Well, if I have 2 tails, that only leaves me 1 coin to come up heads. So that one time I toss heads could be last, it could be second, or it could be my first toss. And the order you list these in does not matter. And then finally, all 3 coins could come up tails. So this gives me my 8 options, or my 8 possible outcomes from my sample space. Now the last example, let's list the sample space for rolling 2 dice. First, I want to find the number of elements in my sample space, the number of possible outcomes I'm going to have. Since I'm rolling the 2 dice, I'm going to draw 2 blanks. With each die, I have 6 possibilities. So if I multiply the 6 times 6, that tells me there's 36 possible outcomes in my sample space. The easiest way to list these 36 possible outcomes is to write them as ordered pairs, where the first element in your ordered pair represents what you roll on the first die, and the second element of the ordered pair represents what you roll on the second die. So let's look at the ordered pair 1-1. That means I rolled a 1 with each die. Then my first die could be a 1 and my second one could be a 2. So I'm going to write that as the ordered pair 1, 2. Then keep the first element of the ordered pair as a 1 and go through the different options for the second die. I could roll a 1, 3, a 1, 4, a 1, 5, and a 1, 6. So that's all the possible combinations of rolling a 1 on my first die and then the numbers 1 through 6 on my second die. Now let's keep this organized. Let's let the first die be a 2. So I could roll a 2 on the first die, a 1 on the second one. So that's the ordered pair 2, 1. And then I could roll a 2 on each die. So that's the ordered pair 2, 2. And then keep the first die as a 2 and then roll 3 through 6 on your second die. So you have the ordered pairs 2, 3, 2, 4, 2, 5, and 2, 6. I want to repeat this process with letting the first ordered pair be a 3, and then a 4, a 5, and a 6, and that will give me my 36 possible outcomes. Well, now let's look at probability. In the examples above, we listed the set of all possible outcomes for the two events, or the single event sometimes if we were just rolling one die. We're going to select one or more of those possible outcomes and consider the probability associated with it. We refer to these outcomes we select to find the probability of as our event. Probability is basically a way of measuring the likelihood of an event. How likely is it that an event will occur? We'll either consider the probability that the event will happen or the probability that it will not happen. Well, I mentioned before probabilities are ratios. So let's look at the ways we can define that ratio. The probability of an event is the number of desired or favorable outcomes. That's the outcomes we want to happen. Those are the outcomes we're considering, divided by the total outcomes. Another way to look at it, it's the number of successes, what we want to happen, divided by the number in our sample space, all the total options. And if we put this in symbols, we say it's the number in our event, E, divided by the number in our sample space, S. Well, consider this fraction. An event is just part of the sample space. So the top number will never be larger than the bottom number of that fraction. Keeping this in mind, we'd see that the probability of any event will always be between 0 and 1. If a probability equals 0, that means the event will never happen. If the probability equals 1, the event will always happen. Well, let's look at two types of probability that we're going to look at in this class. The first is empirical or experimental probability, and it's based on actual experiments. The second one is theoretical or mathematical probability, and it's based on mathematical study of all the possible outcomes of a given event. So with the experimental, we're based on actual data. You go out and you keep track of how many times a certain event happened, and then use that data to find your probability. With theoretical or mathematical, you're just using math knowledge, and we'll look at some examples of that to say if you did this experiment long enough, what should the probability be? Let's begin by looking at a few examples of experimental probability. A study of 500 randomly selected airline flights showed that 430 arrived on time. What is the estimated probability of a flight arriving on time? And give your answer as a percent. Usually with experimental probability, you give your answer as a decimal or a percent. With mathematical probability, you usually give your answer as a reduced fraction. So let's think back to what the probability is. With the probability, we want our desired outcome and we want our total outcomes. For this example, the desired outcome is to arrive on time because that's what I'm asked for the probability of. The desired is always what you're asked for. So the chances of arriving on time, that happened 430 times in this example. Then the total, there were 500 flights that were selected. So the probability of arriving on time is 430 divided by 500. If I divide that, I get 0.86. If I was asked for a decimal, I would stop there. This time I was asked for a percent, so move your decimal 2 places and you get 86%. So 86% of the time, the flights arrive on time. Let's look at the next example. In a survey of college students, 1,162 stated they cheated on an exam, and 2,468 stated they did not. If one of these students were randomly selected, what is the probability that he or she cheated on an exam? And give the answer as a percent. So we first want to find our desired outcome and our total outcomes. This time the desired outcome is what we're asked for. We want the probability that the student cheated. So the number of times this happened was 1,162. Now we want the total. Be really careful with the total. The problem did not give me the total, but my only two options are cheating or not cheating. So if I add these two, I get the total students surveyed was 3,630. So to find my probability, I put the 1,162 divided by the 3,630. If I divide that, I get 0.32 and the decimal continues. Well, I was asked for percent, so move your decimal 2 places, and so it was approximately 32% of the students cheated on the exam. Now let's look at some examples of theoretical or mathematical probability. You roll a single die one time, and let's find the following probabilities. First, let's begin by looking at the sample space for rolling a single die. And if we remember from previous examples, that was 1, 2, 3, 4, 5, and 6. So the number of elements in our sample space is 6. So first, let's find the probability of rolling an even number. So the number of ways to roll an even number is 3. I could roll a 2, a 4, or a 6. And as we mentioned before, the number of elements in our sample space is a 6. So the probability of rolling an even, I have 3 chances out of 6 total. So the probability of rolling an even is 1/2. Let's look at the next example. The probability of rolling a number larger than a 4. Well, there's 2 numbers that are greater than 4, and those are 5 and 6. So the number of ways to roll a number greater than 4 is 2. The number in our sample space is 6. So the probability of rolling a number greater than 4 is 2 out of 6. Always reduce these fractions. 2 out of 6 reduces to 1/3. Now with mathematical probability, if I just roll the die 4 times, based on my answer for part A, we would think that I would roll an even number 2 out of those 4 times, or half the time. And sometimes that happens and sometimes that doesn't. With the mathematical or the theoretical probability, it basically assumes if you repeat the experiment long enough, you should expect to get an even number half the time. So if you just roll the dice twice, that may not happen. But if you roll it 200 times, approximately half of those rolls will land on an even number. Let's look at the next example. The probability of rolling a number larger than 7. Well, there are no numbers larger than 7, so the number of ways that can happen is 0. The number in our sample space was 6, so the probability of rolling a number greater than 7 is 0 out of 6, which is just 0. And if you remember from earlier, we said if the probability equals 0, the event will never happen. And if you're rolling a die, you'll never roll a 7. That will never happen. So we knew from the beginning the probability would be 0. Now the next example, the probability of rolling a number less than 7. Well, every number I roll is less than 7. So without working this out, I know that my probability is going to be 1. That's always going to happen. But let's look at how this happens mathematically. The number of ways to roll a number less than 7 is 6, because every side is less than 7. The number in my sample space was 6. So that means my probability of rolling a number less than 7 is 6 out of 6, which is 1. And as we said, that event will always happen, so the probability would be 1. For our next example, a couple plans to have 2 children. Let's find the number of elements in the sample space first. For each child, I have 2 options, a boy or a girl. So the 2 times 2 gave us 4 total elements in our sample space. And we've listed this before. If you want to list it again, you can. You don't always have to list the sample space, but you do need to know the number of elements in the sample space. Well, let's look at the probability for getting 2 girls. In our sample space, the 2 girls appear 1 time. So the number of ways to have 2 girls is 1. The number of our sample space is 4. So the probability of having 2 girls is 1 out of 4, or 1/4. And if you look at the sample space, the option of GG for 2 girls appeared 1 time out of the 4 possible options. Well, now let's look at the probability of getting exactly 1 of each gender. So that means I want a boy-girl or a girl-boy. So the number of elements in my event, which is 1 of each gender, is 2. There were 2 ways this can happen. The number of elements in my sample space was 4, so the probability is 2 out of 4. Always reduce these fractions. I get the probability is 1/2. And if you look back at the sample space, half of the time, half of the 4 events were 1 of each gender. In the next example, I'm rolling a pair of dice, and I want to find the probabilities. First, I want to find the probability of rolling a pair. If you remember when we listed the sample space for rolling a pair of dice, there were 36 possibilities. So of those, a pair is when you have 1 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So there's 6 ways to roll a pair. The number in the sample space was 36, so the probability is 6 out of 36. If I reduce that, the probability for rolling a pair is 1/6. Now let's look at the probability of rolling the sum of a 9. So think back to all those ordered pairs, and I want to ask myself which one of those add to give me a 9. So first, if my first number is a 3 and my second number is a 6, if I add those two, I get a 9. We'll also want to write 6, 3. These are different. This means my first die came up a 6 and my second one came up a 3. Then I could roll a 4 on the first die and a 5 on the second one. And reverse that, I could roll a 5 on the first one and a 4 on the second one. These were the only options that gave me a sum of a 9. So there's 4 ways to roll a sum of a 9. There were 36 possible combinations in my sample space. So the probability of rolling a sum of a 9 is 4 out of 36. And if I reduce this, I get 1/9. Now I want to look at the probability of rolling the sum of a 4. Well, I could roll a 1 on the first die and a 3 on the second. And reverse that, I could roll a 3 on the first and a 1 on the second. Those add to give me 4. Another option is I could roll a 2 on each dice. I'm not going to reverse the ordered pairs where the two numbers are the same, because that was only listed in my sample space once. If I flip that around, I'd have a 2, 2, which is the exact same thing that I have with this option. So the number of ways to roll the sum of a 4 is 3. The number of elements in my sample space was 36, so the probability of rolling the sum of a 4 is 3 out of 36. If I reduce this, I get the probability of rolling the sum of a 4 is 1/12. In the next example, you have a bag that contains 4 red marbles, 6 blue marbles, and 10 yellow marbles. First, let's describe the sample space for this problem and how many elements are in the sample space. The sample space is just the marbles, the 4 red, the 6 blue, and the 10 yellow. So there's 20 total marbles in the bag. So the number of elements in my sample space is 20. So if I want to find the probability of drawing a red marble, well, my desired outcomes are the red marbles, and there's 4 of those. So the number of ways to draw a red marble is 4. I have 4 chances at drawing a red marble. The number in my sample space was 20. So the probability of drawing a red marble is 4 out of 20, and that will reduce to 1/5. Now I want to know the probability of drawing a blue marble. Well, there were 6 blue marbles, so the number of ways to draw a blue marble is 6. There were 20 marbles in my sample space, so the probability of drawing a blue marble is 6 out of 20, and that reduces to 3/10. Then next, what's the probability of drawing a red marble or a blue marble? There were 4 red marbles and 6 blue marbles, so the number of ways to draw a red or a blue are 10. I've got 10 total marbles that I could choose to fit this probability. There are 20 marbles total, So the probability of drawing a red or a blue is 10 out of 20, and that reduces to 1/2. Next, what is the probability of drawing a yellow marble or a red marble? There were 10 yellow marbles and 4 red, so that gives me 14 marbles I could choose. There were 20 total marbles, so the probability of drawing a yellow or a red is 14 out of 20, and that reduces to 7/10. Look at the last example. What do you notice when you compare parts B and C with part D? Part B was the probability of drawing a red marble was 1/5, and C, the probability of drawing a blue marble, was 3/10. If I add these, I get 1/2. This was the same answer I got to part D. So the probability of a red or a blue was 1/2. When our event consists of 2 or more outcomes that cannot occur at the same time, we can simply add the probability of each event. This is just another way to do this problem. And later we're going to look at some more examples using this. So a formula for this, the probability of A or B is the probability of A plus the probability of B.